Okay, I think that this will be best, more easily understood and comprehensible if I actually give you a real problem to think about first as we talk about the characteristics of this. So let's go to the bottom of your notes that has this problem. And this is the bottom of your chapter 25 notes. Okay, so what we have here is a company that institutes an exercise break for its workers to see if this will improve job satisfaction. Okay, so that's kind of our goal. So if you're thinking through things, what do you think I'm indicating we're going to be talking about from that?
Satisfaction.
Yeah, job satisfaction is going to be what's of interest to us, okay? All right, and that is measured by a questionnaire that assesses the worker's satisfaction. Scores for 10 randomly selected workers before and after the implementation of this exercise program are shown in this table. All right, so what you see is we have a worker number 1 who decided that the satisfaction that that person had was 34. And then here comes the treatment. Then the treatment happens, what's the treatment? The exercise program is the treatment. And so then that same person makes another decision about what their job satisfaction is now. Okay? So you can see worker number 1, had a score of 34, so, whatever the scale is, that's 34, but let's say here at employee number 9, that person only started with a job satisfaction of 15, so for whatever reason, that person is less than half as satisfied or considers themselves less than half as satisfied as worker number 1. Okay? That kind of means something because then this person moves all the way up to 20 after the exercise program. So the point that happens today is that the fact that this is the same person making this number decision before and after, the fact that those are both worker number 1 is important. What's so good about having these same numbers from the same person?
Same bias.
Same biases, very good. Same, same attitude, same general happiness or whatever with their career or their job. Correct. I certainly would not want to compare anything of these numbers, these top numbers, with these numbers down here. Okay, because those people are just like totally in 2 separate realms. So, in summary, what is the thing that is really of interest to us here?
The change.
The change. Very good. I don't care where they started. I don't care where they ended. I care how much change occurred. And so you can see worker number 1 had a change of -1, whereas worker number 2 had a much bigger change at a +5, went up 5. Okay, so this is the only list of interest today. One list only. And is the list about the difference in job satisfaction. Okay, good. All right, so now keep that situation in mind as we go through what our lesson for today is, which is about matched pairs. So, if you know the data that you have are paired, like what we just had, then you can and you should take advantage of that. You should take advantage of that because it really gives you a benefit that you don't have otherwise. So if you have a before group and an after group, then you have the ability to match up the data so that you can compare the same subject before and after. So, can you see that this is going to be a huge benefit to decrease variability? So that's really good. Tyson mentioned that we have, the bias is not now a consideration. The individual happiness is in a consideration. So we have the same qualities. So the foundational traits remain the same for each subject before and after. And so therefore, you have essentially eliminated any unknown lurking variables. Okay? So that is the benefit of having paired data or having matched pairs. Now, since we are only interested in this one list, we essentially do all the computations just like we did a one sample t-test or interval, okay, whatever it is that we do, and we, instead of saying for means, we say for paired data, or for matched pairs, whatever, those two words are synonymous, okay? So we do our conditions then as if we are only doing conditions for this one group here, okay? So here we go. Let's look at the assumptions and the conditions. Random would be stated or assumed that group, that difference, is representative of the population. That group of workers, there's one group of workers, 10 workers that we have. So the sample of those 10 workers is 10%, less than 10% of the population. Fix that, there shouldn't be an S there. Less than 10% of the population of all employees that are going to be on this exercise program. Now, in the past, we've talked about how we want all the people in this before group to be separate and different from the people in this after, or the second group. But does that happen here? No. In fact, they are exactly the same. They are completely related. So the way you talk about this is you don't say that this before group is independent of the after group. You do not say the before is different from the after. You say each pair, so this pair is independent of all of the other pairs. Okay? So each pair is independent of the other pairs. Now, that kind of is like, duh, with this situation where we have a before and after. But let me show you an example that might not be so obvious, that makes it more clear as to why that has to happen. So let's pretend, just side example, that we are talking about the decay of steaks when you put them into Coke versus Dr. Pepper, okay? All right, so we would have one pair. What would I want to make sure? Here's steak A, and here is steak B. That's my one pair. What do I want to make sure about the qualities of those two steaks? They are almost identical in every way possible. Same type of cut, same density, same fat, same size, all that. So this is one pair, and I'm going to put one into Coke and one into Dr. Pepper. Now, if I have another pair, which I need to make sure this pair, those are the same qualities. This better be a third steak and a fourth steak. These two cannot be like a steak A and a steak D. I cannot have more than, one individual in more than one pair. So that's what I'm saying when I say that each pair is independent of the other pairs. Okay. And again, when you have a before and after, that's kind of like a the statement, but there's a case where it might not be as obvious. Okay. And then our large enough condition is identical to the ones we have done in the past. If our sample is greater than 30, then we are super excited because all is good and we can just say it's large enough, ta-da. If it's less than 30, we check and see, and if the parent population is normal or nearly normal, yay, we are good. But if it is less than 30 and we don't know, we don't know about the parent population's qualities, then that's when we make our histogram, and we are making one histogram of what information? This list of differences. One histogram of this list of differences. Okay, so then we have our nearly normal model applies for the differences. And in summary, what's different about this, say from yesterday, where we had two separate groups, now that we only have one, that's supposed to be the word one set of data to consider, which is the differences, we use the computation for one sample test. Okay? Mechanically, a paired t-test is the same as a one sample t-test or interval for means. I've already mentioned that several times. And finally, the sample size is the number of pairs, because this is just one group of 10 employees. So on this problem, our sample size is 10. Okay, yes. Nothing. Okay, so there we go. That's all the basic information. Yes.
Are the hypotheses based on pairs or different?
The difference. Correct. And so that's a good question. The hypotheses and the parameters of interest and everything that we are interested in is based off of this. In fact, if you didn't even tell me this, I'd still be good. All I need to know is the differences. Okay? So I don't care where you started, where you ended up. I just care about the differences. Okay, so let's do this problem here. Identify the procedure you would use to assess the effectiveness of this exercise program. So this is the same situation. Is the exercise program working? And check to see if the conditions allow use of that procedure, test an appropriate hypothesis, and state your conclusion. Confidence interval, or panic, or phantoms. Which is this? Phantoms. Okay. So our parameter of interest. Okay, we were just mentioning. Okay, so we were just mentioning that we are interested in that differences. Okay, what about that difference list are we interested in? What are we going to be inferring about to the population?
Job satisfaction.
Okay, it's going to be about the difference in job satisfaction. But,
From before to after.
okay, from before to after. But in terms of testing, I have to either be talking proportions or means. So what is our measurement? What's my measurement going to be? The average. Good. And I'm going to notate this. It's best if you subtract the after and then take away the before. So let me explain why that is the best way to go. I need to kind of like let me take all this stuff off. What happens is this. If you go 33 minus 34, you get -1. So that means the sign is logical, and it means that from before to after you went down 1. Okay. And so let's do the number 9 person. The 20 is after minus the 15, and that gives me a +5, which is indicating that it went up 5. Okay, so subtracting after minus before gives me signs that are logical and make sense to what happens. All right, so just FYI there. So there's my after, my second one minus the first. And this is the average. What? Average what? Is it the average? Correct. Difference, yes. Average difference. Okay, remember that one list is about the difference that happened. Average difference in job satisfaction of what? What am I going to be inferring to from my sample of 10? Good. Of all such workers, just all of them, of this company, that that participated in the, or that, no, not participated, no, that participate or would participate in the exercise program. So you are inferring that upon identifying what all of the results are from all of the workers that participate in it, then you would be able to make an inference about that group, the average of that difference. Okay, one question before I go further. Am I going to be able to make any conclusion about the individual differences that are occurring? How individuals did in this company? No. My inference is not about individuals. I can't say anything about one person to one person to one person to one person. Those could be all over the place, including I could have outliers. But I am making an inference about the average. Okay, remember? This is a story about the average, not about the individual job satisfaction. Okay, so we got the parameter. Now we're going to do the hypothesis statements. So, the average of the difference. What would that look like in null hypothesis form? That would mean nothing's happening. That would mean that the average of the differences is 0. Good. That means some are above, some are below, but overall, it's pretty much on average, no change. Okay, good. So, the alternative is that the average of the difference. Now, technically, if we looked over here, remember I circled that they were wanting to see if it will improve, so I'm wondering if it is greater than 0 because I want to know if the after increased, got bigger than before. Okay, so this is an upper tail. All right, ta-da! So P and H are done. What's next?
Assumptions.
Our favorite assumptions. So we've got random. Okay, so what about those 10 employees? This one group of 10 employees, what about them? It was stated. Good. It was stated to be randomly chosen. All right, good. So independent. Okay, so I have this one group of 10, and I would say that that's less than 10% of what population?
Participating in that program.
Yep. You know what? I'm going to be lazy right here for time and for room because I actually kind of am running out of room. So for all such workers that participate in the exercise program. So that 10 is surely less than 10% of all such employees that would be working in the or participating in the exercise program. Okay. So what else do I say here? Not one group is independent of the other group, but yep, each pair is independent of the other pairs. Okay, good. All right, what's last?
Large enough.
Our favorite. Okay, is it large enough?
No.
Curse you problem. Okay, well, but wait a second. Is the parent population normal? Grr. No, it's not. Grr. Drat. So, we do not have this. How can I remedy this and feel, okay, that the parent population might be pretty normal and in my histogram? Okay, good. So, let's make histogram. Here we go. What will this be a histogram about? I need to plot these 10 differences. Okay. So, actually, number of workers is going to be here. Yeah, and what I'm interested in is the difference that they exhibited. The difference in job satisfaction. Good. And it's always good to mark the direction you subtracted when necessary, just so there's no question. Okay. So I'm kind of thinking I need to figure out what these differences are, because I don't even know what to do my bins by and put up here yet. I mean, I don't even know the range yet. So I'm going to tell you an easy schmeezy way how to get this entire list without having to go through the subtracting yourself, because you know me, I can't subtract, so that would be just like trauma right there. But especially if you had more than 10 pieces of data, then this could get very cumbersome. And so we are going to use our calculator. And we are going to put our before information into list 1. And we are going to put our after list into list 2. So do that now. Okay, so once you have your data in there, then we want to put the differences in list 3. So we've done this kind of thing before. We have commanded other lists to compute something for us. Do you remember when we would go put our cursor on top of the L3, and then in the past we've said like log of list 1 or log of list 2. Remember we've done that whenever we were transforming. But here I want to tell my L3 to be list 2 minus list 1. So you can see down here what I am commanding my calculator to do. And if you do not have your cursor on top of the L3 right here, then you will get an error. So here when I press enter, voila, all of those differences appear in my list 3, yay, and I didn't even have to do it myself. Okay, and so now let's talk about this list. And we're drawing it. Okay, so here we go. So for this list, I know that I need to figure out what's the span of these differences. What's the range of these differences? They're pretty much going from, it looks like -4 up to 21. So that looks like a range of about 25. How many bins do I want to have at least? At least 5 bins. So what size should I make the bins? Okay, let's make them 5. All right, good. Now, over here, this axis is traditionally the origin. Okay, but I've already drawn it, and I don't want to mess this up. So you know what? I'm going to put a break line right there to notate that I'm doing something different. Okay, and I'm going to actually start right here, just to kind of keep it in 5s. -5, 0, 5, 10, and so on. Okay. All right. So let's fill those things. From -5 up to 0, but not including 0, is -4 and -1. So there are 2 of those. Okay. How about from 0 up to 5? None. There's none from 0 up to 5, because where does this 5 go? This 5 goes in the one that's from 5 to 10. So from 5 to 10 is our 5, our 11, and our 14. So there's...
14.
Oh, 5 and 8 and 14. Oops, my bad. I'm thinking of the next one. Okay. Wow. Okay, how about, let's try this again. I can't subtract. It's all good. I don't know my numbers. Okay, here we go. Am I good so far?
Just 3.
So I still have 3. They are the numbers 5, number 6, and number 8. Okay. Now, what's going to be from 10 up to 15? Which ones do you think there? 10, 11, and 14, and not the 15, because where does that go? In the next bin. And there's only that one from 15 to 20, and then 21 is in the next bin. Okay, so there's my data. Now, okay, let's remember, the goal of this picture is to kind of go through this thought process. I'm thinking that if these 10 pieces of data look pretty, look pretty good, meaning unimodal, kind of symmetric, and no outliers, then I say, oh, I guess the population they came from is probably pretty good looking also. Okay, good looking. Okay, so we want that to be a good looking population. So, what do you have to say about this? Right, it is. And it is unimodal at 3. It is somewhat symmetric. It's not perfect, but it actually is close to perfect, because if this -1 was actually one number higher, it would have been in the 0 bin, and then it would have been perfectly symmetric. So it actually is pretty close to being almost perfectly symmetric. And then there are no outliers, because that is not far enough away, even though we skipped one little bin. So, in conclusion, what?
Nearly normal model applies.
Nearly normal.
Model applies.
Okay, it's a nearly normal model that is applying.
Model almost applies.
Okay, right. It is not nearly applying.
It's nearly almost.
It's nearly normal. Okay, nearly normal. All right, ta-da! We've actually done the worst part of this, the P, the H, and the A. So, what's next? N. Name this test. Name.
One sample test creates
Aha, that's right. For paired data or matched pairs, that's all good. Okay, for paired data. All right, that's the N. Now the T is the test statistic and obtaining our p-value and all that kind of stuff. Since we have our stuff in the calculator, let's go ahead and use our calculator. So, guess what? Stat over to test, and I want you to think about what our options are here. I want to do this one sample t-test. Where do you think that would look? Where do you think that would fall in this menu?
T-test. The second one.
The number 2, the plain one sample t-test. And again, we're using t-test because we only have the sample standard deviation. So number 2 is what we want to do. Number 2 is what we want to do. And so we have the data. So we are in the data, not the stats. And our null hypothesis is 0. Our list is L3. So make sure that you have done second number 3 there to turn it into L3. Make sure your tailage is doing correctly. The sample, we're wondering if the population is greater than 0. Because it's a calculator with a higher operating system that if I drew a picture of it, it would show color. Okay? Calculate. Ta-da! So here we go. Our t-value is 3.6. Our p-value is 0.003. And if you do not tell the reader which curve you're looking at, then they don't know how this was computed. So which curve was this computed from? Degrees of freedom equals 9. Okay, good. You know that every time you have a t-test, you have to indicate which t-curve was used. Okay, 9 because it's n minus 1. All right. Now, okay, what's next? We're getting down to the end. Obtain your p-value, which we know that our p-value of 0.003 is less than our alpha of 0.05. So then our decision is, since our p-value is low, the null hypothesis has to go. That's right. Our null goes. And let's do our conclusion. And I want to, go through this carefully, make sure that any little word intricacies that you get correct. So here we go. Yes, we start with, since the p-value is less than alpha, I reject that. Okay. What are you rejecting? Correct. Just state this null hypothesis in words. Okay? You're rejecting that did you say average difference? Okay, and you also could put true just to emphasize this is about the population. The true average difference in job satisfaction is 0 of all such employees, whatever. By the way, if you did not put this word in here, it's wrong because you are not able to conclude and infer about individual differences, just the overall average. Okay, so therefore, I what? Yep, I have evidence that what? The alternative is true. The average difference in job satisfaction is greater than 0. I might make sure I've answered the question. Did it ask anything specifically? Yeah, you want to assess the effectiveness of the exercise program. So since that was our only variable, we probably are feeling pretty okay but you know, I hesitate to say this is the reason because there still could be something else going on there. But I mean, if it's a controlled experiment, we should be able to say causes. So this appears to mean that the exercise program is what? Is effective. We just want to leave that blank. In improving average difference of blah, 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 whatever. Okay, we'll just leave that naked right there. All right, very good. So again, you are just making sure that you know this is about the average, not about the individual job satisfaction. Okay? So here we go. Estimate with a 96% confidence the average of job satisfaction. So say that the company says, woohoo, it's working, it's good. Well, how much is it really improving? So is it worth us paying our employees to go get a 30-minute break to go exercise? You know, is this making them that much happier that it's worth paying for? So let's see how much happier they are. So we want to estimate that average difference in job satisfaction. So what about the parameter and assumptions? Yep. Parameter and assumptions are stated above. Okay, so I just got to do the N, which is, name this thing. So 1, sample, T, interval, 4, paired data. Okay. Now, interval. We have this already in here, so let's just go pop this puppy out. Stat over to test. And so I want you to think about that menu for a minute. It looks like number 8 is a plain T interval. All right. Our data is in list 3. And make sure your confidence level is 96 because that's what we were asked to do. Calculate. So, we got this interval here, 2.83 to 14.17. And how did you compute that number? Degrees of freedom? 9. Okay. All right, so I tell you what, I want to pause for a second and see if you can write the correct conclusion, and then we'll check and see how you did, because you should know enough by now to be able to kind of accomplish that. So, let's let you have a second to do that. Pretty? But let's see how you did.
It's not about what's on the inside.
It's not about what's on the outside. That's right. Okay. Huh. Oh, I know what's going on. Okay, here we go. Ready? I am 96% confident that the true average difference in job satisfaction for all such employees is between 2.83 and 14.17 points higher after the exercise program. You might have not had this, but what this is really indicating when you put this here is which one is the higher. I mean, if you don't put that, you're not saying which one is the higher and what happened. Okay? And, of course, since this is about a difference, since 0 is not in the interval, this further indicates that there actually is an average difference. Okay, and one quick thing before we stop on this, remember that the ones that you have to make a 0 statement about are 3 things. A confidence interval about 2 means, that's yesterday's stuff. A confidence interval about paired data, that's today's, because I want to know about the difference that has occurred or is occurring. And a confidence interval that we did a long time ago about 2 proportions. Those are the 3 times that you have to do a 0 statement. Okay, so I think then your homework is actually not quite as long as last night's. Okay, so